Okay, I'm going to take a look at section 6.4. This is method of sections. So this is another approach to uh, analyze truss structures where you want to find the forces in members that are connecting, the long thin members that are connecting together. Okay, so here's some applications, but this is kind of what we saw in the previous section, right? Use trusses for things like cranes, towers, right? So when we actually went through and did the method of joints, it required us to go through and analyze like each joint one at a time. And it took a while before we actually could get to, or potentially took a while before we could find the forces in the middle of a large truss, right? Middle meaning, away from the supports, right? The furthest away from the supports, okay? So we have another approach, method of joints. Okay. Okay. I'm sorry, method of sections is another approach. Method of joints was the approach we did. Okay, so here's an example. So we'll take a look at and see how this works. All right, for the first part of your analysis, what you're going to do is you're going to solve it just as we did with method of joints. Okay, so you consider the entire structure, you perform an analysis so that you can solve for the unknown reactions. Okay, so like the reactions at D and E, right? So these are pin. This is a pin. This is a roller support. So there's a reaction, normal to this surface here, another one normal to this surface here, and one parallel to the surface. So there's three unknown reactions, but we can come up with the summation of forces and the summation of moments about some point, and we could actually, with those three equations, we could figure out what the reactions are here, okay? Well, it's the same approach you use for both method of sections and method of joints, okay? It's the same thing. Where it differs is what you do is you take part of your structure, okay, and you divide it. So like this is a line. Basically, it says, I'm cutting it right here, just sort of conceptually, not really. And what you're going to do is you're going to analyze some portion of it. You might analyze like whatever's here on the left or whatever here is over here on the right. Okay, you might analyze either parts of those, and you're going to look for the unknown values. Okay, now the way it works is this. Let's say that you were looking to find, I don't know, force between B and C, let's say, or the forces on this member between B and C. So after you'd gone through and done the entire structure, you did the analysis to find the reactions, you would cut it here. And the reason you chose B and C is because that was the unknown, maybe that was the unknown one that you wanted to find, the forces in this member, right? Or G, CG, or GF, or something like that. One of the three, or all three, potentially. Okay? So what happens is that instead of doing like an analysis at A, then at B, and then at G, let's say, or coming from the other direction doing C, F, doing analysis of multiple joints, we can actually just perform method of sections once and then solve for these unknowns. Okay, and the way it works is this. Let's say that we have this section over here. So everything kind of to the right of this line here, or this, I don't know, cutout, whatever you want to call it. Everything over to the right here, okay? Now, the way you can think about it is that this part over here, to the left of it, applies some forces to this part. And they are done through this beam here, or this member here, and this member here. So as far as this part of the truss is concerned, all it sees is a force pushing or pulling along between here and here, another force here and here, and another force between these two. So it sees these three external forces, of course, and the reactions over here. So it sees everything over here basically just looks like these three forces, okay? So if we cut this right here, what we can do is solve for these three unknowns. So we don't know what these are, right? We don't know what this one is, we don't know what this one is, and we don't know what this one is. So I have three unknowns, okay? So with that in mind, if you have three unknowns, what you can do is when you're doing method of sections, you also have moments now because not everything is acting at a single point, right? So we have the summation of the forces in the x direction, summation of the forces in the y direction for this part of the structure. And we also have summation of the moments about every point equal to 0. So we now have three equations that we can use, okay? And that's going to be the way we're going to look at it. So, you know, if you're trying to solve a problem where like maybe you want to solve at the ends, or maybe where the forces are applied, or at the reactions like here and here, maybe it's D, E, E, F, or you know, some that are closer to the supports. Method of joints works out really well. It's a nice and simple way to solve it. But when you're going further out, further away from the applied forces and further away from the supports, then method of sections is a simpler approach. Okay, and that's basically what this is talking about here. And of course, it applies the equilibrium principle and Newton's third law. Right. So that's what we're going to do. We're going to take a look at using method of sections. Okay. So here's the steps for the analysis and for this particular truss structure. All right. So first thing is, you know, you can go and let me see, where do they do the analysis? Okay, so this doesn't show you the entire analysis, but it shows you how you could break this thing apart. So in this case, there's a cut right here, and you have a truss structure over here, and you have another one over here, okay? And notice that as far as this one is concerned, it sees all of this as just these three forces acting along here, here, and here, okay? As far as this part of the structure is concerned, it sees one acting here, one in this direction, one in this direction, and then, of course, the three out here. And we have this one, too. But as far as what they are, as it sees the other part of it, it sees it as just this force, and this force, okay? So it really doesn't matter. As far as analyzing this part, it doesn't care really what's going on here. It's just these three forces, okay? Okay. So you go and decide, where do you decide where you want to cut it? You base it on where you need to determine the forces and where the total number of ohms does not exceed 3, okay? So you're going to use that to choose where you want to cut it, okay? And then you decide which will be easier to work with, right? So in this case, you know, it's like, okay, if I wanted to find these three forces in here, you could decide either over here or over here, whatever you want to work with, okay? And this one might be easier. I see only one external force here. Okay. And if required, determine the internet. This is the equations of equilibrium by drawing the FBD and doing the entire truss. Okay. So, you know, a lot of times I see this is done first, you know, before you actually go in here and do these. You may not be required to do that. Like I said, if you solve it over here, you might be good just by doing this and with these three unknowns. Okay. All right. Okay, so, and then, of course, the free body diagram of the part of the cut truss. All right. Okay, so, you know, it might be that you have two free body diagrams, one when you have the entire structure and one when you have the cut one, like these. All right. And it's before, you know, you can do them all as tension or compression. It doesn't matter. In this case, at least from G's perspective, so if we're looking at point G or looking at point D, it doesn't matter however you want to solve it. This one looks like it's pulling away from C, so it's under tension. This one's pulling away from C, under tension. And from G's perspective, it's pulling away, okay? So let's keep going. Okay. And then, of course, you apply the scalar equations to solve for it, all right? And same idea, you know, however you draw the forces, whichever way you decide to draw them, if your answer comes out positive, you drew it in the right direction. If it comes out negative, it's in the opposite direction, okay? So if you thought they were all tension, if you thought they were tensions, like from G's perspective here, if you thought it was a tension, it became negative, then it's really a compression, okay? Okay. So, like I said, most cases you can come up with one equation. So you may be able to solve for everything with one equation. All right? Okay, so here's an example. Take a look at this one first. Okay, so first part we can recognize here. They're looking for KJ, KD, and CD. So these three members here. You could have, you could have used method of joints, then solve like here, here maybe, then here, and then maybe you could have gone, or you could go, then you could have gone to here, L, then K. So you could have like five sets of equations solving for each one of these joints for the unknown forces. And then from that point, you could solve for these. When you're solving here and here, you could solve for those. Okay. But in this case, what we could do is we can actually just come up with, we could do, solve the entire structure. Okay. Pick which section you want to work with. In this case, the author chose the left. And it looks like, the left is a little bit, maybe a little simpler. You have two forces here. You have two reactions here. This one you have a force here. And you have a reaction here. Okay. And then, so we'll determine these. You can determine their support reactions. Then you use the equations. Okay. So first part here, find your reactions, right? So we find the reactions. So we're doing the entire structure, okay? Well, if we look at AX, if you notice there's no other, this is a roller support, there's no other force there, so AX is going to be 0. And then we now have AY and GY, okay? So you could do the summation of the forces in the Y direction. And then, of course, you're going to have 1, 2, 3. You have these three forces acting down. And you have these two acting up. So we still have an unknown. We have two unknowns and one equation. So what we would need to do is do the moment equation. Okay. All right. So here it is. Here's AX. The author chose to do it about G. So doing the moment about G, you're going to have 1, 2, 3, 4. Now you don't, well, AX is 0, so it doesn't matter, but you had to have four pieces, 4 moments acting in this equation, okay, for equilibrium. So the first one, AY times 12. Okay, so it's 12 from here all the way over to here. And it causes, if it was to push at this point, it would cause clockwise rotation about this G. Okay. And then it would cause clockwise rotation. The only thing I'll tell you here is that one part of this you should say, the author chose it as being clockwise as positive. Didn't make a note of that. But typically when we solve them, just to follow our standard, is we do it in the reverse of this, okay? Which you'll find out that it doesn't matter. In this case, it might be confusing if you were trying to figure out like what the reactions were at the end by following this. But in general, we would say this is negative and these are all positive. But since it's equal to 0 over here, right, it doesn't really make any difference, okay? So in this case, solving, you got the other one, so the author calls this one positive for clockwise, and then the counterclockwise ones you made negative. Like I said, it doesn't matter. They would show up on the other side as positive, and positive one side and positive the other. So here's the 20 times 10. So from here to here is 20 times 10. 30 times 8. So from here to here is the 30 times 8. And 40 times 6. From here to here is 40 times 6. And like I said, typically we use it as counterclockwise is positive and clockwise is negative. He just refers for whatever reason, but it works out. It'll work out both ways, okay? Just got to be consistent. Okay. Okay, so now from that, we now have 56.7. So now we know what AY is, all right? And then you can use that to solve for the others. I'm sorry, for G. And in this case, since we're doing this part of the structure, we really don't even have to worry about what's going on at G. So you could just write it as, moments about G to solve for AY. Okay. So we only need these reactions because we're connected across by these three members. Okay. Since we chose this side. You could have chose that side also. I don't think it'd be that much of a difference. Okay. So here we go. Here's the reaction. Okay. Here is the split. So this is the section. This is split. So now you see, what do we have? We know what AY is. We know what this force is going down here, and C is given. So now we have these three forces here. Okay, these three unknowns. Okay. So you can do the same thing. You could do summation of the forces about, the X and the Y component. You could solve for those. You could just say, well, in this case, you could say this one, and this one all together are equal to the Y component of this, right? And then the X component, you know that FJKJ is equal to the negative of FCD, okay? So we could have also, we could do it. We could also do that, all right, if we wanted to. That's another choice, okay? All right. So the first part of this, what we'll do is we'll do the moment. And the only thing is you wouldn't know, like in this case, it's like one of these is going to be in the, well, you also have this, right? So you have this, and you also have FKD, right? So you have 1, 2, and then the X component of this guy right here also. So that's another approach. You could do the summation of the forces in the Y direction, summation of the forces in the X direction, and you could solve for the unknowns, okay, the two equations. Or, as the author chose here, and you notice the author did counterclockwise this time as being positive. So the author chose D, point D, to do the analysis for this, okay? And you can pick this. He picked a point, a pivot point outside of this actual outside. You could do it inside, you could do it outside, but the author chose a point outside of this, the actual section. So where these forces come together and meet here. So at point D, okay, you could have done A if you wanted to. It may have been simpler. D is nice because you have this force and this force acting together. And now you'll see everything's at 90 degrees. Like this one's at 90 degrees, 90 degrees, 90 degrees, 90 degrees relative to something that's connected. So this is all X, all Y, all Y, all Y. So it makes the calculation a little bit simpler this way. Okay. So at point D, and like I said, you could have chosen anyone. You could have chosen at point A if you wanted to. B, C, doesn't really matter. D is good because we have two forces coming in there to meet. And that eliminates two of them, right? Because they meet at that point. So, but you can choose, you have a choice to choose here or somewhere else along the structure. Okay. Okay, so if you do that, you're going to have how many moments? 1, 2, 3, and 4, right? These two forces don't do anything. Okay, so first one is minus 56.7, minus because it goes clockwise around D, okay, plus 20 times 4, which is from here to here, would cause counterclockwise rotation about D, and this is plus 30 times 2, which is the same thing. It would cause counterclockwise about D, and then minus FKJ times 3 because from this point, this would cause clockwise rotation about D, okay? So the only unknown at this point is FKJ, okay? So now that you know FKJ, you can use that to solve like FCD, okay? So the next step, summation of the, okay, so the author did the summation of the forces in the Y direction, okay? So like I said, you could do that. Or you could also find like FCD in the other one, but there'd be two unknowns in that equation. So okay, so we'll follow this. FY. So you'll notice that in the y direction, we know this one, we know this one, we know this one. So the really only one left is the y component of this guy here, okay? So the way you use it, law of similar triangles, square root of 13, right? Because it's 2 times 2, 3 times 3, so 9 plus 4, square root of, and the square root of that. So this is like the hypotenuse, and this is the, let's see, where's our angles here? So it's the adjacent side, okay? So that's the vertical component, okay? Times kj, fkd, okay? So here we are. Here is our, here's our reaction at A. Here's our force at B pulling down. Here's our force at C pulling down, and these are negative and negative. And then this one is also pulling down, right, the way it's drawn. So FKD is just, if you go and solve this, FKD is 8.05 kNewtons, okay? And then we can do summation of the forces in the x direction, right? So same thing here. So we know that it's 8.05 times 2 over 13 because it's this side, right, of the triangle here, this side over the square root of 13 times the magnitude of the force, which was this, minus 66.7, okay, and that was previously, let me back up, that was this, the FKJ, okay. Right, and then it's the FCD off in this direction, so you just add them. All right, and the reason this was minus 66.7 was because, remember we had solved it, what we recognize is that the force really is not going to the right, it's going off to the left, okay, which means that at this point, this beam, because it's pushing into K, this beam is under compression, okay. So that one, you could write it either way. If you write it as minus, you could have reversed this, but probably better not to. Just leave it the way it is. And then when you put FKJ in the equation, all you do is substitute in for it with minus 66.7 kNewtons. And here it is. Okay. So, you know, your choice, MD. You could have chosen something else if you wanted to. Like I said, D. FD is the best one here, right? Because and you could always, you know, pick a point off of this, but D is pretty good. It's like the next it's the joint that essentially connects two of the forces here. So it's like gives you a pivot point. And that's one way. Like I said, you could have also done it as some other point. You could have done it, you know, summation of the force in the x direction, summation of the force in the y direction also, and use that equation and then substitute it in. This works out well. It's very quick, short. Okay, your three equations, you solve for the three unknowns. Okay. All right, here's another problem. Okay, next problem. All right, so this one, same thing. We're going to use method of sections. And we're looking for ED, EH, and GH. Okay, so ED here, EH here, and GH. Oh, okay, so we know we want to cut it right here. Okay. And, you know, just looking at the problem, you recognize that appears this side is going to be a lot easier than working with this side over here. Okay. And then we can pick probably, you know, maybe we'll pivot around H here. That looks good. Okay, so what we're going to need then, we're going to need to find this, the reaction here, the normal reaction. Okay, so we'll have to go through and think about like the entire truss structure, right? Looking at these here, you know, the 30 pound, 40, this really doesn't, you know, this is in the x direction. Well, there's no reaction in the x direction from this one, right? We're going to have, there's a 40 kN going down here, 40 kN going down here. So in the y direction is what we care about over here. So these are going down. And then we have reactions here in the y direction and the x direction, right? So we can use that to potentially to help solve what this is here, right? We don't know you know, we don't know how much is over here and how much is over here just yet. Okay, until we solve for that. All right. So, like I said, we're going to cut through these. We'll look at the left section. It's easier. And we need to determine the support reactions at F, right? We need to determine this, of course, because that'll be part of our, we need to know all of our support reactions and all the, or if you want to think about, really need to know all the forces that are external connecting our section, right? Draw the free body diagram, then apply the equations, okay? All right, try to do so every equation yields an answer to unknown. Yes, we care. We'll do it that way, okay? All right, so first part. Determine the support of the reactions F by drawing the free body diagram of the entire truss. All right? So the way the author chose here is like, well, pick what point do you pick? Well, in this case, pick A. Because with this, if we pick A as the point to determine the moments about, is that we have two unknowns we can eliminate. So there's only one unknown, all right? And you'd have to think about like, okay, so what's going to be acting at this point? We're going to have a force, draw this straight through its line of action to be acting at I. We have another one acting at H. This one comes straight down through and meets the point, so there's no moment due to this one. So we have one at 1.5 meters, one at 3 meters. So here's my 1.5, that's this one, 1.5 from here. Here's the force at 30 kN acting at 3 meters from here. And then we have, you know, draw the line of action straight down to this one. And then that's acting at 2 meters from this. Okay, that's that one. And then F of Y, we draw the line straight down here. And we find that this is actually 4 meters. A line that intersects with it at 90 degrees is 4 meters from here. Okay, so that's this. And in terms of the directions, you know, the author wrote is the way we typically do is, you know, the plus direction is counterclockwise. So this would cause rotation in the clockwise direction. This and all the rest would be counterclockwise. This would cause counterclockwise, counterclockwise, and this would cause counterclockwise about this. So it would go around like this. Okay. So just solving for F of y, sub y is 57.5. All right. Okay, so now we have the reaction there. So we're going to have these three unknowns. Okay. So from this point, I'll just follow through. Draw solving at M of E. Okay. And like I said, you know, you have a choice. Here you can see it's the same kind of thing. You could do it at G. That might be beneficial. But notice E. If you do it at E, what do you have? These forces go straight through it. And this 40 kN goes straight through it too. So you're just eliminated three forces. So your equations are simpler at this point. So the only thing we got left is this one, which caused clockwise rotation about this. And then a force along GH, if you draw the line straight through, it's acting at 1.5 meters in the counterclockwise direction. Okay? So with those two moments due to this force and a moment due to this force, this is in the clockwise direction, the 57.5, which we found out before, times 2 meters. And then the 1.5 times FGH, which is counterclockwise. So now you have FGH, right? So the next thing the author did is did summation of the forces in the y direction, right? So if we look at it, we have this one in the y direction, this one in the y direction, and then the y component of this, all right? Which is just going to be 3 over, this is 3, 4, 5, right? 3, 4, 5 triangle, so it's going to be 3 over 5, right? And we look at the directions. This is down, it's negative. This one is down, it's negative. And this one is up, there's our positive. So here is the solution for FEH. Okay? Now, the next thing the author chose is there's one more unknown to get here, and it's FED, right? So the author chose to do it around H, and this is one of the places I said was a good place to do is H. Could use that as the pivot point because these two forces meet there. These two I already know, so I can pull these out and make it simpler. The equation could be simpler if I eliminate them by doing it there. So these two acting over here at this point. And then we're going to have FED. We're going to have this force and this force. Okay. So the three forces acting at H, relative to H, we could do 1.5, okay, from here to here, times FED, and that's clockwise, so that's going to be negative. That's the negative one right here. And then we're going to have the 40, and if we draw this one straight down, we'll see the distance from here to here is 2 meters. Not shown in this diagram, but from G to here, draw this straight down, it's 2 meters from G to H. Okay, and that would cause counterclockwise rotation about H. So you could pick any of these points over here as long as, you know, the members are the unknowns that you're looking for are connected to them, or these forces are connected to it, and you can use those points. Okay, so then the last one, of course, is this one, 57.5, and that would cause clockwise rotation about H. So that one is negative. It comes out to be negative. All right. So the end result is minus 100 kilonewtons. And if you look at it, FED, we drew it as a tension pulling away from point E. Okay. Well, it turned out to be negative. So now we know it's really a compression. And like you said, you can write it like these. If you write it like this, then there's no, like, it really doesn't matter kind of what your free body diagram has it drawn. If you write it as tensions and compressions, then there's no need to look back at the free body diagram. There's enough information contained within the answer here and here. Okay. And the other one. Oh, here. Right. That's under tension. Okay. So that's basically it. So that's it for at least the lecture slides of section 4.